Hey students, in this video we're going to discuss exponential functions, logarithmic functions, and inverse functions. What we're going to do is review the properties of exponential functions, logarithmic functions, and the properties of inverse functions. All right, so let's get started. An exponential function, it has the general form of f of x equals b to the x. For this in our logarithm function later on, we're going to have f of x equals 2 to the x. And we'll make a small table of values over here. So we're going to have x, and we'll have f of x. And we'll only deal with the positive values right now. So when x is 0, we're going to get 2 to the 0, which is 1. When x is 1, we're going to get 2 to the first, which is 2. And when x is 2, we're going to get 2 squared, which is 4. So if we hop over to Desmos for a moment, let's turn a lot of this stuff off. Okay. So if we look at our graph, I think we may actually be able to make a table from this. Let's see. Table, we'll put x, and here we'll put f of x. So f of x is not going to let me. Too many variables try to find an x. Oh, I'm sorry, f of x1. My bad. Cool. So then if we put in 2, we'll put in the values that we just put in. So we have 0, 1, 2, 3, 4, 5, 6, even though we won't actually see some of these on here. Okay, so all these green dots correspond to the integer powers of 2 that we know. So we have 0, 1, 1, 2, 2, 4, and 3a. That's going to be enough. So for an exponential function, all we're doing is multiplying a base by itself x times, and x is just our exponent. So some of the fundamental properties that we should know are the first one is if I have the same base and different exponents and I'm multiplying, we can just add the exponents. For instance, if we had 2 to the 5th times 2 to the 8th, that's just 2 to the 8 plus 8 plus 5. We'll say 5 plus 8 to be consistent with how we wrote it. 2 to the 5 plus 8 is 2 to the 13th power. If you ever want, and so then the next property we have is if I have the same base and I'm dividing, I can subtract my exponents. So if we have, we'll say 2 to the 8th, we'll make these 2 small so we can actually see what's happening. So we'll say if I had 2 to the 5th divided by 2 squared, that's going to equal 2 to the 5 minus 2 power, which is 2 cubed. Now, the reason for this is 2 to the 5th is really 2 times 2 times 2 times 2 times 2, and 2 squared is just 2 times 2. So in the numerator, we have a lot of multiplication. In the denominator, we also have multiplication. And we know when we're simplifying a fraction, we can take out the things that are commonly multiplied. So I can take out a 2, and then 2 2's in the numerator and 2 2's in the denominator. And that's just going to leave 3 2's in the numerator and a 1 in the denominator. So that's how we get our 2 cubed. Similarly, if I have b to the m to the n power, so I have a power to a power, we can just multiply the exponents. So if I had 2 cubed squared, that's really equal to 2 cubed times 2 cubed, which is going to be really just 2 times 2 times 2 for the first set of 2's, and 2 times 2 times 2 for the second set of 2's, which is going to give us 6 2's altogether. So 2 to the 6. The shortcut is we could multiply the exponents. So one thing that's going to be true for all basic exponential functions is the domain is all real numbers. And we can, and the range is going to be 0 to infinity. And we can see this on the graph that we have for some common exponential functions. So we have 3 to the x, 2 to the x, and 3 halves to the x. Notice that the graph really gets close to 0 when x is a very large negative value, and the graph grows large when x is even slightly positive. So the graph, when the base is greater than 1, what we have is exponential growth. And when the base is less than 1, what we have is called exponential decay. All right, so when the base is actually, the base has to be between 0 and 1. And so we'll see that on this next graph down here. And so we have these bases 1/2, 2/3, and 1/3. All of those bases are between 0 and 1. And so that's what we call an exponential decay function, because as the exponent gets larger, the output value is going to be smaller, because like say we're multiplying by 1/2 several times, then the result is going to be that we get a greatly diminished value as x gets larger. And we can hop back over to Desmos to actually see that as well. So right here where we have f of x is 2 to the x, we're actually just going to change this to be 1/2. Oh, I put 11 halves. That won't work. So we're going to have 1/2, and we'll put some parentheses around this. So 1/2 to the x power. And so now you see that table of values that we made, right? So we have 0, 1, 1.5, 2 and 1/4, 3 and an eighth, 4, 1/16, 5, 1/32, and 6, 1/64. So those are incredibly small values. And again, we can see that as x gets larger, we get almost to 0, almost to 0. It's not exactly 0, and we'll talk about that when we actually do calculus. All right, so, oh, wrong thing. So that's a quick review of exponential functions. So in general, when we're talking about the exponential function compared to the logarithm is the inverse of the exponential function. And that's going to be true because the exponential function passes the horizontal line test. And the horizontal line test says that if a horizontal line intersects a function exactly once, then that function has to be invertible. So conveniently, the logarithm is the inverse of the exponential function. The basic form for logarithm is we have the log, we have a base, and we have we'll call this our argument, and the output is an exponent. So when we see something like log base 2, we'll say 32. So that's going to equal 5, because we could rewrite this logarithm to be the exponential equation 2 to the 5th equals 32. So logarithms output exponents. And so like they answer the question, 2 to what power is 32? So the basic property, so because logarithms are essentially exponents, they have very similar properties to exponents. So when I'm multiplying inside of a logarithm, I can actually just add the two factors of the product. So if we had something like log, we'll say 2 times x, that's the equivalent of having a base 10 logarithm of 2 plus a base 10 logarithm of x. And remember, when we have a logarithm and we don't write the base, so say we had like f of x equals log x, this implies the base equals 10. It's called a common logarithm. Now, if we actually write the base, then the base is whatever number we specify. So like in this case here, this is a base 2 logarithm because we put a 2 as the subscript. So generally, when we're talking about like properties and stuff, we're just not going to write the base because it's just easier. So next is if we're dividing inside of the logarithm, if our argument contains division, then we can subtract the numerator, give a logarithm for the numerator and subtract the logarithm of the denominator. So say we had something like log, we'll make it something fancier. So we'll say like log of x squared divided by cosine x, for instance. So this would give us the log of x squared minus the log of cosine x. And that's it. And so the last thing is we could have the argument raised to an exponent. And when that happens, you just move the power to the front. So say we had, we'll say the log of x to the 7th. So that's going to equal, now we'll use this first property. So we know that, we'll actually use the property as exponents. We know that the log of x to the 7th, you know what, make this a smaller thing. We'll say x to the 4th. So this is easier to write out. So we'll say that's the same as having the log of x times x times x times x. And we know from the first property where we multiply inside the log that that just means that each factor of the product gets its own logarithm. So that's like log x plus log x plus log x plus log x. And that's since we're counting the same thing, that's really just for log x. But from here to here, we could have just moved the exponent to the front. So that's just a shortcut for doing this. So these three properties of logarithms will help us in calculus when we're doing logarithmic differentiation, or we're doing the derivatives of like the natural logarithm is going to be a thing that comes up. And so lastly, there is a special logarithm that comes up a lot in calculus and pre-calculus. It is the logarithm that has a base of e, Euler's number. It's so special they give it its own logarithm, and that is the natural logarithm of x. So when we see log, you'll never see log base ex because it implies this logarithm, and this always has base e. And e is Euler's number. It is 2.71828, I believe, off the top of my head. So E, yeah, 2.71828182846. That is the base of that logarithm. All right, so moving ahead, uh, we'll come back to this example in a moment. So because logarithms are inverses of exponential functions, the domain and range are going to just flip. The range for basic exponential functions is 0 to infinity. So we'll make a note here. This is the range of, I think we called it b to the x. And this is the range for the logarithm is the domain of the basic exponential function. And just like the point 0, 1 is on the graph of all exponential functions, the point 1, 0 is on the graph of all logarithmic functions. All right, so let's go back to this example. So We're going to use those three properties of logarithms that we had to expand this so that everything in the argument has its own logarithm. So first, we're going to write an equal sign. So we're going to continue our equality over here. So because we have a fraction, the first thing that we can do is give the numerator its own logarithm and give the denominator its own logarithm. So the cube root of y is equivalent to y to the 1/3 power. Cool. So the next thing that we can do is, because in the first logarithm we're multiplying, we can give each factor of the product its own logarithm. So we have log base 2 16 plus log base 2 of x to the 5th. And we'll just keep that minus log base 2 y to the 1/3 the same. So we're moving our powers at the same time. So in our final step, we ask ourselves, is 16 a power of 2? Is there an exponent that we can raise 2 to get 16? The answer to that is yes. 2 to the 4th power is 16. So this entire logarithm turns into a 4 because they're equivalent. So then for the x to the 5th, this exponent, the 5, can move to the front. So that would give us plus 5 log base 2x. And lastly, the 1/3 can also move to the front. So that's minus 1/3 log base 2 of y. So we're not going to do a problem where we have to condense the logarithm, because in calculus, we generally use the logarithm to expand to make the problem easier, and we're never really going backwards to make it more complicated. But say we actually began with this step. Now, the 4 won't actually be helpful here because uh, you it you'd have to intuit a lot to turn this back into log base 216. So imagine for a moment this doesn't exist. If we had 5 log 2x, the first thing you would do to condense this is move the 5 back as an exponent, move the 1/3 back as an exponent for the y, and then that would take you to this step. And from that step, we just go up. But like I said, we won't actually do that in calculus. We always use the logarithm to expand instead of condense. All right, so next is us solving basic exponential equations. If we have to use a logarithm, we're going to use ln. Even though using the base of one of the numbers would be easier, we're going to use ln because we use it a lot in calculus. So for example A, we have 4 to the 3x minus 4 equals 16 to the x. So we can express 16 as a power of 4. So we're going to have 4 to the 3x minus 4 equals 6. So 16 is the same as 4 squared, and the 16 was raised to the x power, so will 4 squared. So using our properties of exponents, that's going to tell us that 4 to the 3x minus 4 equals 4 to the 2x. Now, if you've learned this before, you know that they're going to say, like, because the bases are equal, the exponents have to be equal. But what's really at play here is that if you put a logarithm on both sides, so we have like the ln of 4 to the 3x minus 4 equals the natural logarithm of 4 to the 2x. Anytime two things are equal, the logarithms of those things have to be equal. And so the property of logarithms is that you can move the exponent to the front. So that would be 3x minus 4 times the ln of 4 equals 2x times the ln of 4. And we can divide the ln of 4 away. And so we end up with this equation where we have 3x minus 4 equals 2x. And if we quickly solve for x, we will get x equals 4. I'll let you go back and check that, but x equals 4. We subtract 2x, add 4, and that was solve that. In example B, we have 5 to the 3x plus 1 equals 11. So first thing we can't express 5 as a power of 11. 5 to the what equals 11? No easy number. And similarly, 11 to the something equals 5. Also not an easy number. So no easy number exists for this. So when we can't easily express a number as a power of something else, we just use logarithms to make the problem easier. So let's do the ln of 5 to the 3x plus 1 equals the ln of 11. So property of exponents, the 3x plus 1 moves to the front. We'll have ln 5 equals the ln of 11. So there are two ways to work this. One way is to get the exact answer, and one way is to get an approximation. So let's get two approximations for the ln of 11 and the ln of 5. So ln 5 is 1.6, we'll say 1.61, and the ln of 11 is 2.4. 1.61, 2.4. So the ln of 11 was equal to 2.4. The ln of 5 was 1.61. Cool. So what we really have is 3x plus 1 times, so we'll say 1.61, 3x plus 1 equals 2.4. So 3x plus 1 is equal to 2.4 divided by 1.61. And so 3x is equal to 2.4 divided by 1.61 minus 1. And finally, that's going to give us x equals 2.4 divided by 1.61 minus 1, all divided by 3. Cool. So let's just put all that in the calculator. So we had fraction first. So 2.4 divided by 1.61 minus 1. And parenthetically, this all needs to be then divided by 3. So that's 0.164. So x equals 0.164. Cool. All right, that's one way to work it. In class, we'll talk about the other way to work this, where we distribute the ln of 5 and ln of 11. But it's this is a lot easier once we have actual numbers substituted in. All right, so last thing is inverse functions. Two functions are inverses. Two functions f of x and g of x are inverses if you can take one function, substitute it into the other, and get the input value, and you get x. So we'll see an example. Let's go back over to Desmos for a moment. So instead of having 1/2 to the x, we're going to have, we'll do something that we all know, x squared, and then we'll put the square root of x for g of x. We'll delete that, delete that, delete that, and we'll take out this table. We'll turn this on. All right. So if we move over here, turn on some of the controls. Do I have a point? Gotta take my points out. Oh no, they're all here. Did I have f of x, a to, yeah. So if we look at our graph, hold on a moment. Let me open up the other thing. Yeah, so we're back. So let's make this x squared and make this the square root of x. Give me just a moment. Square root x. Cool. So what it means for two functions to be inverses is if I put an output value from one function into the other function, I get the value that I get the input. I get the value that gave me the output value. So right now on the parabola, we're at the point 3,9. Like right here, we're at 3,9. And on the square root of x, the blue graph, we're at the point 9,3. Notice the x and the y just switch around. A key property of inverse functions is that they are the same distance from the line y equals x. The horizontal distance for the parabola to this line is the same as the vertical distance for the square root function to this line. It's also going to be true that if we took the distance from here to a point like exactly on the line, we'll get the same thing. But visually, this we can see as x moves out, the distance between the line y equals x and the parabola and the square root function grow at the same rate. So that's what makes them inverses. The trick for finding the inverse of a function is to swap the x and y, solve for x, and then, swap the x and the y's, solve for y, and if the algorithm is algebraically possible, the end result is going to be the inverse. So for this example, we want to find the inverse of y equals 2x minus 1 divided by 3x plus 2. So first, we're going to get x equals 2y minus 1 divided by 3y plus 2. First thing we can do is multiply the 3y plus 2 to the other side. So that's going to give us x times 3y plus 2 equals 2y minus 1. Next, we have to distribute our x. So that's going to give us 3xy plus 2x equals 2y minus 1. The next thing we need to do is group the y's on one side, the x's on the other. So we get 3xy minus 2y equals negative 2x minus 1. Cool. So the last thing that we can do is factor out a y because it's the greatest common factor on the left, and that's going to give us 3x minus 2 equals negative 2x minus 1. And since we want to solve for y, we can divide both sides by 3x minus 2. So we get y equals negative 2x minus 1 divided by 3x minus 2. So if you ever want to know if you properly found an inverse, my recommendation is to substitute in a point and see what you get. An easy point to choose is choose x to be 0. So when x is 0, and we're going to substitute 0 into that function. So when x equals 0, y is negative 1 divided by 2. So what that means is on this graph, the point negative 1 over 2, 0 should be there. Let's see if that's true. So we'd have negative 2 times negative 1/2 minus 1 divided by 3 times negative 1/2 minus 2. And so that's going to be 1 minus 1 over negative 3 halves minus 2. So that's going to give us 0 over negative 7 halves. And that's 0. So it's indeed true that when the point 0, negative 1/2 exists, on the inverse, we have the point negative 1/2, 0. So for this last example, we'll talk about this one in class. I don't want the video to get too long, and I think I'm at a pretty decent length right now. So we will do this one in class. All right, I'll see you guys in class. I'm sorry the video's kind of long. A lot of information though.